Good afternoon, everyone, and let us start the session. So, I will be mainly presenting on the topic biofouling management, more focusing on the Indian Ocean region and the maritime industry, and we'll discuss on what are the key challenges, the solutions which exist, and the innovation and the way forward as well. So, let us begin by asking the first basic question. So, what is biofouling actually? So, biofouling usually refers to the progressive accumulation of many biological organisms on a submerged or water exposed surfaces. And this usually occurs particularly in the marine and freshwater environments. And this process almost begins very instantly right after the surface is immersed and usually evolves through many multiple stages. It starts with the adsorption of organic molecules, then it is followed by microbial colonization and eventually leads to the attachment of many larger organisms such as algae, barnacles, mussels, and tubeworms as shown in the picture below. So the major impact of biofouling is very significant in the maritime industry, and we will be focusing on major aspects such as the emissions increase, the invasive species vector, the port vulnerability, and the infrastructure degradation. So the accumulation of these biological organisms on the ship hulls increases the surface roughness, which disrupts the hydrodynamic flow around the vessel. So even thin layers of slime can increase the hydrodynamic drag by around 10 to 15%, while severe macrofouling can raise the resistance by 30 to 60%, which forces the ships to consume more power to maintain the operational speeds. This increase in resistance caused by the biofouling also directly translates into a higher fuel consumption. Moderately fouled vessels often experience fuel penalties of around 15 to 20%, and in some extreme cases, fuel usage can rise well over 40%. So, for larger commercial vessels operating continuously on international routes, these penalties amount to millions of dollars annually, in addition to the fuel costs. The increased fuel burn also leads to proportionally higher emissions of carbon dioxide and other pollutants, with biofouling related inefficiencies usually contributing to around 35% increase in the CO2 emissions per voyage. This poses a significant challenge for compliance with increasingly stricter IMO regulations, including the Energy Efficiency Existing Ship Index, which is the EEXI, and the Carbon Intensity Indicator, which is the CII. So, beyond these fuels and emissions, biofouling also negatively affects the vessel speed and schedule reliability. So, what happens is these foul ship hulls can suffer speed losses of up to 1 to 2 knots, which disrupts the shipping and voyage planning, the port schedules, and the charter party agreements. And to compensate for this, operators may usually increase a significant amount of their engine loads, further accelerating the fuel consumption and mechanical wear and tear. Biofouling also drives up the maintenance and life cycle costs. So the presence of fouling organisms usually accelerates the coating degradation, and it promotes what is called as MIC, which is the microbiological influence corrosion. So they create somewhat like a localized corrosive environment on the hull surface. So, and this results in more frequent hull cleaning, earlier coating failure, and increased dry docking requirements, which usually raises the maintenance cost by up to 40% over a shipping vessel's operating life. In addition to this technical and whatever economical impacts biofouling has, it also plays a major role in the spread of invasive species and aquatic life. Foul shippers usually act as very good vectors for transporting organisms across biogeographical regions, which means leading to a overall ecological disruption and the introduction of stringent biofouling management regulations in most of the several countries. And non-compliance to these can result in port delays, mandatory cleaning and checks, or usually a lot of financial penalties. Critical underwater components such as the propellers, rudders, sea chests, and thrusters are also very vulnerable to the biofouling process. Fouling on these propellers alone can reduce the propulsion efficiency by 8 to 10%, while fouled sea chests can restrict the cooling water intake, increasing the risk of engine overheating and unplanned downtime. These factors collectively elevate the operational risk and reduce overall vessel reliability. So overall, to summarize, biofouling has a very significant impact and many hidden inefficiencies in the maritime industry and maritime sector. And its combined effects on the fuel efficiency, fuel consumption, emissions, maintenance, and the regulatory compliance impose usually tens of billions of dollars in the global economic losses each year. Particularly, it is more significant for the vessels operating in warm and tropical waters. Coming to the parameters which influence tropical biofouling, there are majorly four subcategories of this, which is the environmental parameters, hydrodynamic parameters, the surface and material parameters, and the biological parameters. So the environmental parameters usually include water temperature, nutrient concentration, salinity, dissolved oxygen, solar radiation, which and all these factors combined directly control the biological growth rate and species composition. And among these, the temperature and the nutrient concentration is one of the most influential and the primary dictating factor in the speed and the extent of the fouling development. Then we come to the hydrodynamic parameter, which includes the flow velocity, the turbulence intensity, and the residence time. And they also play a very critical role in determining the attachment and detachment behavior of the fouling organisms. Usually, low to moderate flow conditions encourage organism settlement, while turbulence influences nutrient transport to the fouling layers and affects fouling system and morphology as well. So the next one is the surface and material properties, which usually include the surface roughness, the wettability, surface energy, and the material type. So these in combination govern the initial adhesion part of the microorganisms and the stability of subsequent biofouling layers. The rougher and more high-end surfaces generally exhibit a much larger or greater fouling intensity and susceptibility. And finally, coming to the last one, which is the biological parameters. They include usually the microbial growth rates, the larval availability and settlement cycles, the species interaction, and the competition among the different fouling species. So the interaction of these parameters usually results in a faster initiation and the uh, initial stage of the biofouling, also the sustained growth and increased severity of the fouling in the temperate and the tropical waters. So the next major important discussion is about the significance of biofouling and its comparison between the tropical and the temperate waters. So as we can see from the figures below, the intensity, the accumulation and the colonization rates in the tropical regions is much more severe as compared to the temperate waters. And the major reason for tropical fouling to dominate and be more intense compared to temperate waters, the major factor is the temperature. The severity usually lies in the temperature as a primary driver. This happens because the typical temperature range in the tropical region is usually around 25 to 30 degrees Celsius compared to the 5 to 20 degrees Celsius in the temperate waters. And what happens is at these elevated temperatures, the microbial metabolic and reproduction rates can increase drastically up to 2 to 3 times for every 10 degrees Celsius rise, and which significantly shortens the time required for fouling initiation. And what happens is, as a result, the initial biofilm layer formation in tropical waters can occur within a day or two of the surface immersion, whereas for a similar layer to be formed in the temperate water, it usually takes around 1 to 2 weeks. And this rapid biofilm formation accelerates the transition from the microfalling to macrofalling, enabling a very early settlement of algae and many larvae to settle on the submerged surface. The next major important part is the consistent conditions and the biodiversity available in the tropical falling. So nutrient availability further intensifies the falling dominance and also can increase the microbial biomass density, usually up to 3 to 4 times compared to the temperate water region, which in turn strengthens the biofilm stability and enhances the macrofalling settlement. Biodiversity in the tropical region also plays a very crucial role. So the tropical marine environments host up to 40 to 50% of higher species diversity of fauning organisms than the temperate regions. And this increases the larval availability and reduces the colonization delays, which allow multiple fouling species to attach simultaneously. Also, studies have shown that the microfouling coverage on the unprotected surfaces, usually in the tropical waters, can almost reach up to 90% surface coverage within a span of 3 to 4 months or 3 to 6 months. Whereas for a similar type of coverage in the temperate waters, this might usually take a year or 2 years. And tropical waters also support something called as a year-round biological activity because there is no seasonal interruption compared to the temperate waters. So what happens is in the temperate region, the region and the geography usually experience winter temperatures that reduce the fouling organism activity by around 50%. And this provides a natural fouling reset in the temperate waters. And the absence of such a temperature-driven die-off or a reset in the tropical region allows for the falling layers to persist continuously, leading to a thicker and more complex falling structures over time. From an operational standpoint, the impact is very substantial. So for ship hulls, which usually operate in the tropical waters, biofouling can increase the hydrodynamic drag by up to 40%, which results in the fuel penalties of around 30 to 40% eventually. So to deal with the biofouling process in the shipping industry, usually we rely on a mix of anti-fouling technology and combination of many chemical, physical, and operational strategies to control this process. So the most widely used approach right now is the application of anti-fouling coatings on ship hulls and submerged structures. Traditional biocidal coatings typically were based on copper or zinc compounds, and they function by continuously releasing many toxic agents that inhibit the settlement and growth of fouling organisms. More advanced self-polishing copolymer, known as SPC coatings, also gradually erode during the vessel operation, exposing the fresh biocide layers and maintaining anti-fouling performance over time. In addition to these, there is something called as foul release coatings, which are based on silicon and fluoropolymers, and they are being increasingly researched and used currently. These coatings do not kill the organism directly, but instead reduce the adhesion and cohesion strength, allowing for the fouling organisms to be removed through hydrodynamic forces when vessels operate at sufficiently higher speeds. Alongside the mentioned anti-fouling coatings, there is something called as mechanical and operational methods. So this usually covers what is called as in-water hull cleaning, periodic dry docking, and optimizing the sailing speeds to to manage the fouling accumulation from time to time. The last one is physical and the emerging technologies. These usually include ultrasonic systems and electrochemical systems, UV-based treatments, and air lubrication technologies, which are being explored currently. So while some of these approaches show a lot of promise, their adoption remains still limited and they're often used as a supplementary measure rather than a standalone solution. So overall, the current anti-fouling practices are usually they focus largely on preventive measures and preventive ways and maintenance oriented. And their primary aim is to slow down the falling rather than eliminate it entirely. So, despite the widespread use of whatever I mentioned on the existing anti-fouling methods, they face a lot of several critical limitations. And one of the most significant challenges is the environmental impact. Usually, what happens is the biocidal coatings release a lot of toxic substances into the marine environment, which affects the non-target organisms as well, and this contributes to a long-term ecological damage in and around the surrounding. So this has already led to the global ban of highly effective compounds such as tributyl tin and the increasing regularity restrictions on copper-based biocidal coatings as well. Then there is something called as the performance limitations. They also persist. The effectiveness of the anti-fouling coatings degrades over time and is highly dependent on the operational conditions such as the vessel speed, the international route which is taken, and the idle duration. So foul release coatings, for example, are very ineffective for slow moving or stationary vessels, which are common in offshore and port-based operations. The mechanical operations like the in-water cleaning, while necessary, can also damage the coatings to an extent and promote faster regrowth of fouling if not carefully managed. From an economic and operational perspective, anti-fouling strategies are largely reactive rather than predictive in nature. So the maintenance schedules are typically based on usually fixed intervals rather than actual falling severity, leading to either a premature intervention or excessive falling before action is taken. This results in a lot of increased operational expenditure, sometimes unplanned downtime, and uncertainty in the performances and optimization. And furthermore, the current methods also lack adaptability across varying climatic and environmental conditions, particularly more often than not in the highly aggressive tropical waters. Given the ever-changing ecosystem and the climatic environment, there is a much growing need to simulate the whole biofouling process to better understand, predict, and also sort of manage the biofouling behavior to a large extent. Biofouling is, as I mentioned, a very dynamic and covers a lot of stages. It's like a multi-stage phenomena, and it's usually influenced by many factors which I've mentioned, such as the environmental factors, hydrodynamic, material, and biological parameters. So the simulation of the biofouling process enables the integration of all these factors to predict when fouling initiates, how it evolves over time, and how severely it can impact a particular vessel's performance over time. By simulating the fouling growth and its interaction with the fluid flow, so it becomes very much possible to create a time dependent change in the hull roughness, the drag coefficient, the fuel consumption, and emissions. This allows the ship operators to move from a very reactive based maintenance to a condition based and predictive maintenance strategy. Also, simulation enables the virtual testing of these anti-fouling coatings as well, and the materials which we can use for creating different anti-fouling coatings under changing operating and environmental conditions, which also helps us to minimize the cost of trial and error approaches. And from the sustainability and regulatory standpoint as well, the biofouling simulation supports compliance with the IMO efficiency and decarbonization regulations. So by quantifying the performance penalties and associated with the fouling process and evaluating the mitigation strategies. So importantly, to say the simulation process reduces reliance on environmentally harmful biocidal solutions by enabling the development of a more optimized, route-specific and an eco-friendly anti-fouling strategies. Regarding the simulation one, previous research has been explored the simulation of a biofouling process, but this has occurred usually primarily in the temperate marine regions, where fouling development is strongly influenced by seasonal variation. So a notable example was a research paper which I read on the time-dependent biofouling growth model developed and conducted at the University of Strathclyde in the United Kingdom. So this study utilized the operational data from commercial shipping vessels, which were operating mainly in the temperate North Atlantic routes, with falling growth rates reflecting the seasonal characteristics of mid-latitude waters. And the model which they used represents biofouling as a time-evolving process, converting the falling accumulation into equivalent surface roughness parameter to predict the increase in the ship resistance and the power demand needed for the particular vessel. However, the key part was the environmental conditions which were considered in this work are largely representative of the temperate and the subtropical region, whereas falling growth slows significantly because there is a offset and cooling period in the temperate region. So as a result, while such models demonstrate the feasibility of simulating the falling and the evolution of the falling process, they're not very directly transferable to the tropical region where the temperatures are usually very high and feasible and there is uninterrupted biological activity. So currently at MRC, we are trying to develop a five-stage biofouling simulation framework. What we have done, we have understood that biofouling process is not just a very instantaneous event, and it comprises of many multiple stages, which are governed by the interaction of many of the surface chemistry and biological reactions, fluid flow, and biological activity. So many existing approaches simplify fouling by representing it just as a function of fixed roughness or resistance term, which limits the ability to predict how fouling evolves over time and under different varying environmental conditions. So at MRC, our current work focuses on addressing this particular gap and by systematically trying to simulate the entire biofouling process in a much more detailed, staged, and physics-based manner. So to achieve this, what we have done is we have split the entire fouling process into five different stages, and all these things are sequential yet interconnected to one another. So the stages are the first stage is the condition. The first stage is the conditioning film formation. The second one is the biofilm initiation. Then we have the biofilm maturation, the microfouling development, and the macrofouling establishment. So each stage, what it does is modifies the surface properties and surface chemistry and the hydrodynamic environment, thereby directly influencing the progression into the next stage. This decomposition allows us to introduce complexity at each particular stage gradually and helps us to validate individual processes as well. So this is a representation of how we have decomposed the five stages. So first we have the film formation, then the bacterial and diatoms addition, then the further development of the biofilm. Then we go on to the micro and macrofouling. So the first stage is the conditioning film formation, which occurs almost immediately after a surface is submerged in seawater. So usually organic molecules such as proteins, lipids, and most of the polysaccharides submerged present in the seawater are rapidly adsorbed onto the bare substrate within seconds to minutes. And although this stage does not involve any living organism, it plays a very critical role by chemically and physically modifying the entire surface properties. So the conditioning film changes surface energy, the wettability and charge of the surface, creating a much favorable foundation for the microbial attachment and effectively preparing the surface for subsequent biological colonization. Then we have the second stage, which comprises of biofilm initiation, where the free swimming bacteria approach the conditioned surface. So bacterial transport toward the surface is governed by the hydrodynamic forces and chemostatic responses to nutrient gradients. And upon contact, these bacteria secrete adhesive proteins that allow a sort of irreversible attachment, and this is followed by a secretion of something called as EPS, which is the extracellular polymeric substances, which form the initial biofilm matrix. And at this stage, the surface transitions from a chemically conditioned layer to a more biologically active interface. And as the bacteria population grows over time, the process enter the stage called as the biofilm maturation stage. And bacterial cells multiply and organize into a multi-layered and a spatial heterogeneous structure. And nutrient and oxygen gradients develop across this biofilm thickness, with oxygen concentrations decreasing towards the interior part. And this leads to very something called as a metabolic specialization, where the interior bacteria shift towards something the it's called as an anaerobic metabolic pathway, and the EPS matrix, which was secreted before, becomes much more denser, providing a much more mechanical stability and protection against hydrodynamic shear stress, chemical exposure, and antimicrobial agents. The fourth stage is the microfouling development stage, and it is characterized by the settlement of microorganisms such as diatoms, microalgae into a more mature biofilm. So these photosynthetic organisms exploit the biofilm's nutrient-rich and adhesive environment. And as the microfouling progresses, the species composition evolves in response to the environmental conditions such as light, the temperature, and nutritional availability. And this stage significantly increases surface roughness and creates a sticky textured surface that enhances the likelihood of larger microbial and microorganism attachment. Then the final stage is the macrofouling establishment, where the larger organisms such as barnacles, bryozoans, mussels settle and grow on the fouled surface. So what happens is the larvae detect the biochemical clues emitted by the biofilm and the microfouling layers, which trigger the subsequent settlement of these larger organisms. Mussels usually anchor themselves using their basal threads, while barnacles and bryozoans permanently cement to the surface structure. And in tropical environments, this stage can progress extremely rapidly, with hundreds of bryozoans and thousands of barnacles usually establishing within just 2 weeks. And over time, these organisms form a complex and interactive sort of following ecosystem, which is highly resistant to the removal and has a very severe hydrodynamic and operational consequences. So the simulation process, let's discuss about the progressiveness, complexity, and the integration strategy. So the initial plan is to begin the entire simulation with a very sort of simplified physics equations at stage 1, which will enable the validation against the experimental data. Then we will use each subsequent stage and their output parameters from the previous stages as an inputs. So because of that, we can increase the complexity gradually. We can go from smooth to rough fall conditions. We can go from a uniform to a very spatial varying following distributions. We can go from a deterministic predetermined model to a more probabilistic biological behavior. And the modular structure too allows a very independent validation of each stage, easier incorporation of new biological or environmental parameters, and adaptation to different regions such as the temperate, subtropical, and the tropical regions. So this is a depiction of the stage-to-stage integration and feedback loops of the subsequent biofouling process. How we go from stage 1 to stage 3 to stage 2 to stage 2 and 3 to stage 4, then subsequently to the stage 5. So what happens is from stage 1 to stage 2 coupling, we usually have the conditioning film properties determine the bacterial attachment probability. As we go from the stage 2 to stage 3, the initial biofilm characteristics affect maturation rate and final density. Then as we move to the stage 4, the mature biofilm matrix provides a much more better substrate for the diatom colonization. And at last, when we go to the final stage, which is the macrofouling stage, the microfouling derived settlement clues trigger the macrofouling species such as the barnacles, bryozoans, or the mussels per further. So before we look at the equations which were used for the simulation process, we need to account for something called as the major important part, which is the Q10 thermal scaling, which usually focuses on how we account for the temperature. So biological reaction rates are very temperature dependent, and the model which we are using uses a Q10 coefficient as a relationship to adjust the biological rates according to the surrounding water temperature. So in this equation, the rate T, which is the biological rate at the current temperature, while rate at the reference temperature, T reference, represents the baseline rate. And the Q10 describes the sensitivity of the biological process to a 10-degree change in temperature. The important point is that the temperature correction does not create a separate fouling stage. Instead, it modifies the rates at which the biological process will occur. So this is particularly important in the tropical waters because warmer conditions can accelerate the biofouling growth and therefore accelerate the overall biofouling process depending on the region. So let's discuss the equations in much more detail. So for stage 1, which is the conditioning film, the first stage uses the equation as follow. So what happens is when a clean hull is immersed in the seawater, organic molecules begin to adsorb onto the surface. So the first term, which is the KACB tau max minus tau, it represents the adsorption term, and the term tau max minus tau is important because this represents the remaining available surface. So initially, almost the entire surface is available, so adsorption can occur very rapidly. As the surface becomes increasingly covered, the available surface decreases over time and adsorption slows down. The second term, which is minus kd tau, it represents the desorption term, meaning that some of the molecules which were already attached to the surface leave subsequently over time. So therefore, the equation essentially represents a competition between the molecules arriving at the surface and molecules leaving the surface. And eventually the system approaches an equilibrium standpoint where the conditioning film becomes relatively stable. Then once the conditioning film is completely formed or is stable, then the bacteria start to attach to the surface. So the first part of this equation represents the bacterial attachment. It depends on the bacterial availability in the surrounding and on the presence of the conditioning film. The most important part of this equation from a maritime perspective is the exponential term, which is given by e power minus tau w by tau c. So this represents the effect of something called as wall shear stress. As wall shear stress increases over time, this exponential term decreases. Therefore, the bacterial attachment becomes less favorable under very high shear conditions. And in practical terms, a vessel traveling at a relatively higher speed can experience stronger hydrodynamic shear stress near the hull surface, which can make the initial attachment more difficult. Then we have the second term, which represents the detachment of bacteria that have been already attached. So overall, the complete equation balances the bacterial attachment against the bacterial removal rate. Then for the third stage, which is the biofilm maturation, what happens is at this point, bacteria is no longer simply attaching to the hull. They become developing into a much structured biofilm with extra EPS helping the community remain much more attached to the hull surface. So the first term of represents the contribution of the attached bacterial population to the formation of the biofilm, and the next major part is the monod kinetics, which is given by S by Ks plus S, and this majorly represents the nutritional limitation. What happens is when nutrient concentration is extremely low, the growth rate is strongly limited. And as a result, the nutrient concentration increases, the growth rate approaches to its maximum potential. Then we also have the logistic growth term, and which is given by 1 minus x by x max. So this prevents the unlimited growth of the biofouling stage. As the biofilm approaches its maximum capacity and capability, the growth slows down gradually. And finally, we have the Q10 factor, which incorporates the temperature dependence, while the final term represents a biofilm loss. So this complete equation captures what is the major idea that the biofilm growth depends on, which is the bacteria, the nutrients, the temperature, and available surface capacity. So the first stage is the microfouling stage. So to sum up this equation, it's nothing but nutrients plus the availability of sunlight plus temperature plus the carrying capacity and minus the loss. So the first stage usually represents the microfouling, particularly the colonization of much larger algae and diatoms. This stage is different from the bacterial growth because the photosynthetic organisms such as the algae and the diatoms require both nutrients and sunlight. And this is represented by the minimum function which is given here, minimum of the concentration by Kn plus concentration, and the I represents the intensity and Ki is the half saturation parameter of light. So this function implements the idea that the growth is limited by whichever resource is available and is more restrictive. So for example, if let's say nutrition is available in high amount, but light availability is extremely low, then the algal growth is still limited because one of the parameters which are necessary for the growth is not in the required quantity. Conversely, also, if let's say the sunlight is abundant and there is insufficient nutrients, then that also can restrict the growth. And this equation also again includes the Q10 temperature scaling, which is the main carrying capacity term. And also we have a loss term which is given by KSAM. So therefore, this stage connects the biological model to environmental variables such as nutrient concentration and solar irradiance. So the final stage represents macrofouling such as barnacle settlement, bryozoan settlement, and mussel settlement. The important biological assumption here is that macrofouling is much more dependent on previous biofilm stages. And this is represented by the following equation, exponential term 1 minus e power minus x by x reference. So what it does is as the biofilm biomass increases, this term increases, meaning that a mature biofilm creates a more favorable sort of environment for the macrofouling settlement. At the same time, the second exponential term, which is the e power minus tau w by tau c, it accounts for the hydrodynamic shear stress. High wall shear gradually makes settlement more difficult. Finally, the last term, which is negative of mu dn, represents the mortality or loss of the macrofouling organisms. Therefore, the final stage effectively converts the earlier biological development into a much large-scale fouling that has direct engineering consequences to the ship operations. So the problem which we faced while simulating the entire biofouling process is that solving this entire complete system repeatedly is very computationally expensive. If we incorporate using something called as computational fluid dynamics model, it will take a lot of time and it will be extremely expensive because each simulation will require solving multiple coupled differential equations which span over a large period of time. And instead of doing this every time, we wanted to have a prediction which uses the physics model to generate a large synthetic data. So what we have done is we generated an 80,000 scenario data set using Latin hypercube sampling. So the advantage of using Latin hypercube sampling, also called as LHS, is that it provides a very broad coverage of the parameter space rather than randomly concentrating simulations in only a very small region. So the resulting simulations become the trading dataset for multi-output random forest. So random forest is the machine learning model which we have used that learns the relationship between the environmental and biological inputs and the resulting falling outputs. Once trained, the random forest can produce predictions in less than a millisecond, making it a much more suitable for a large scale or a real-time application of the falling process. So coming to the results, one of the interesting factors to note is using the validation in the validation one is that the R square value is not equally high at every stage of the simulation. As we notice here in the microfouling coverage percentage at around day 5 and days to 50% microfouling. So the R square value is relatively around 0.39 and 0.36 and the validation status reports as a fail. But this doesn't directly imply that the model is not working accurately. So what happens is at the early early time points around usually around the day 3 or day 5, many of the simulations have already reached a very similar biological state. So what happens is this creates something called as a variance collapse. So I guess let me just give you an example. So let us imagine we have let's say around 80,000 simulations or around 50,000 simulations, but almost all of them produce approximately the same microfouling value. Then what happens is we are accounting for a case that is which has very little variation for the machine learning model to explain. So this can make the R square value appear relatively low even when the absolute prediction errors are very small. Therefore, for the what happens is for the lower early stage R square, therefore what we do is for the lower early stage R square values, we do not automatically interpret it as a failure of the random forest surrogate model. The most important result to look at is that the validation results which are obtained in the long term or the long run endpoint are pretty much accurate. For a drag increase, the random forest achieves an R square of approximately 0.9973. And for a macrofouler density, the reported R square is approximately close to 1. So this means that the surrogate is reproducing the long-term outputs of the physics-based model with extremely high agreement. And from an engineering perspective, these endpoint predictions are particularly important because the drag increase and macrofouling are the quantities that ultimately determine the operational impact of the fouling. So therefore, the results which are demonstrated that the computationally expensive ordinary differential equation model can be approximated very accurately by a much faster machine learning surrogate model. Currently, we have also been looking at a wide range of research topics to understand the biofouling process in detail and also to account for the increasing complexity from present in different biological and biogeographical regions. So the first topic which we are majorly looking at is how monsoons drive the marine biofouling in the Indian coastal region. So this project usually focuses on understanding the influence of the Indian monsoon on the marine biofouling in the coastal waters. And the study explains how seasonal changes caused by monsoon, including the variations in the salinity, temperature, turbidity, nutrient levels, dissolved oxygen, and rainfall, impact the growth and success of the biofouling communities. So the ultimate goal of this research topic is to develop a sort of conceptual framework that can support a future predictive model for forecasting biofouling intensity, enabling better maintenance planning and more sustainable biofouling management. Then the next one, which focuses on the parameter sensitivity analysis of the simulation framework. So this project, what it does is it applies a global Sobal-Saltelli sensitivity analysis framework to evaluate how variations in different environmental parameters, including temperature, salinity, oxygen, and nutritional content, affect the model prediction. So, in addition, a local one at a time sensitivity analysis is also being performed on the biological rate constant within each stage, which is used for the simulation of the biofouling process. Then, the last an important topic is the biofilm maturation and the recruitment dynamics. So this project examines what is the relationship between the biofilm maturation and the recruitment of the macrofouling organisms in the tropical marine environments with a much deeper focus on the Indian Ocean region. Biofilms are usually very complex microbial communities and which form on the submerged surfaces, and they play a very critical role in determining whether the larger fouling organism, which is the macrofouling stage, such as the barnacles and mussels, successfully settle and establish. Although the biofilm age is often usually used as an indicator of maturity, what we notice that recent research suggests that the additional factors, including the extracellular polymeric substance, the production, the microbial diversity, the community composition, and quorum sensing activity may also have a very significant influence on the larval settlement and the recruitment success. That is it for the important topics which we're currently trying to discuss on how we can subsequently increase the complexity and create a much realistic simulation of the biofouling process. So moving forward, our main aim is to increase the fouling complexity by researching and incorporating different biological equations. Further, we want to develop a fully coupled multi-stage biofouling simulation model for the major ports in the Indian Ocean region. Then we also want to apply and calibrate the model for the Indian coastal regions according for the varying tropical environmental conditions, including the seasonal changes and monsoon rains. And at last, we want to enable the prediction of a time-dependent falling growth, drag penalties, hydrodynamic drag, and operational impacts using the surrogate model. Thank you, everyone.